Thanks. I'll begin by saying that I'm also a biologist, but unlike the last speaker, I'm going to try and talk mainly about maths, I suppose. That's quite dangerous for me. I'm sort of in awe here at the moment because for those of you who understand the English education system, my highest qualification in maths is that I scraped a pass at grade E in A-level. So a corollary of that, I think, is that as I walk the plank here, my talk is going to be full of assertions, many of which are not proven, and many of which might be in error. But I'd be grateful to find out if that were the case. Okay. So as a kind of overview, I'm going to talk about consensus methods and supertree methods. In particular, I've been interested in consensus methods for a long time, and in the 90s I developed some extensions, I suppose you could call, to what I'll call classical consensus methods here. And I'm going to introduce them and talk about how they and the classical methods might be generalized to the supertree context. I've always been a bit surprised, in a way, that the development of supertree methods, the supertree problem being a generalization of the consensus problem, hasn't led to the generalization of the existing well-understood consensus methods, which may have served us quite well for some time, but seems to have led more to the proliferation of other methods, some of which, at least I think, are quite ad hoc. So I'm going to introduce a kind of, I'm going to introduce the reduced consensus methods as I'm going to characterize them in a way that presents them as a within consensus generalization of consensus methods. And then I'm going to talk about how we can generalize to supertrees, both the classical and the reduced methods. I'm going to show a few simple examples, because I can only deal with simple examples. And then I'm going to try and address the question of which of the properties generalize, which of properties that we might use perhaps to define the methods in the consensus context are generalize in a useful way to the supertree context. And I'm going to particularly there focus on loose supertrees, which is a synonym of semi-strict. You'll see why I use a different name a bit later on. I'm also going to talk a little bit about what the meaning of this concept is. Okay. So, for those of you who don't know, I presume most of you do, consensus methods take as input a set of objects of some kind, such as phylogenetic trees, and they return a consensus object of the same kind that represents the trees, the input trees, or is a synthesis of them, or as we heard earlier from Alan's talk, is an inference from them. And there are a range of different kinds of methods. Over here I've mentioned a couple, the strict and the loose, or the semi-strict method is a synonym for it. And in these methods we get a conservative summary, or a conservative inference if you prefer. And by that, I mean it doesn't resolve any conflict in the input trees, it represents only the agreement. So the two splits that are in this consensus are the splits that occur in every input tree. They're what would be true if any of the input trees were true. It's also another way of thinking about conservative methods is that they're insensitive to the weights given to the information in the set of trees. They just depend on what information is present in there. And alternatively, there are more liberal approaches which are sensitive to the weight or the arbitrary repetition of particular input trees, such as the majority rule method. And you can see here the majority rule tree includes an additional split that's present in all three of these. Just to clarify the difference between strict and loose or semi-strict methods, they only differ in the consensus case when some of the input trees have polytomies that are resolved in some way by some other trees. So, for example, if we were to collapse this blue branch in this tree, the corresponding branch here would be collapsed in the strict consensus because it's not in every tree, but it would be in the semi-strict or loose consensus because it's not contradicted by any tree and it is present in some. Okay, so this is a sort of motivational slide that explains sort of where I'm coming from, at least in terms of consensus methods. And here we've got a couple of input trees. Okay, they're very simple. And down here we've got a consensus tree. This tree is the Adams consensus, which Adams described his method in 1972, and it's the grandfather of all methods. The strict consensus and the loose consensus in this case is nothing. It's a bush. I haven't bothered to put it up there because it conveys no information. The Adams consensus tree looks a bit better than that. It's conveying something, and it seems to correspond partly with what we can see is in these trees. To be more precise, these trees share the fact that A and B are more closely related to each other than they are to C. This is a greatest agreement subtree. It's also a reduced consensus tree, a tree in which taxa have been removed in order to represent the agreement that exists amongst the input trees. One of the problems with the Adams consensus tree is that its interpretation for biologists. For a long time, it seemed to be that mathematicians quite liked Adams consensus trees because they're Pareto on triplets. They have every triplet that's present in every tree. The problem is they also have triplets that aren't Pareto, and we can't really distinguish between the two. So, for example, for biologists, there's a question of how do we interpret this Adams consensus tree? If we say that it's telling us that all the trees agree that A and B are more closely related to each other than they are to C, and that all the trees agree that A and B are more closely related to each other than they are to D, then it's lying to us, because that's not true. If we interpret it, in fact, we can see that if we change round the labeling of D and C on these input trees, we end up with the same Adams consensus. In fact, if we take those two and the two with the alternative labelings, we also end up with the same Adams consensus tree. So for a biologist looking for things that you can interpret as things that are more closely related to each other than something else, Adams trees are a bit problematic. And we have to interpret this in the way that Adams described in 1986 as a tree that shows that A and B nests within A, B, C, D, is higher up the tree. Its last common ancestor is higher up the tree. The last common ancestor of A, B is higher up the tree than in A, B, C, D, and that can be satisfied in a number of different ways. And it means that the information content of this is actually paradoxically less than this, despite the fact that this has more taxa in it. So Adams consensus tree is a bit of a problem. And also strict and loose consensus trees are a bit of a problem because there's some information here and those trees are completely unresolved. Okay, so over the 90s I developed some methods which I called reduced consensus methods, and I'm developed them in certain ways, but I'm going to try and present a way of thinking about them that I think will be helpful because my ultimate aim is to generalize those methods, as well as the classical methods from which they're derived, to the supertree context. So what I've been trying to do is come up with a way of presenting them that is most useful for that generalization. I should emphasize that I'm not talking about how these methods might be instantiated. I'm not talking about algorithms at all. I'm only really talking about definitions. There may be some problems with these definitions, and if anyone notices any, I'd be very pleased to hear about it. I'd be upset for a little while, but I'd be very pleased to hear about it. Okay, so I'm introducing them as a kind of within consensus generalization, which I think is a nice way of thinking about them. And we can define, for example, a set, we'll call it strict star, as the set of all the strict consensus trees for each set of trees induced from the set of the input trees by the power set. So we can remove any leaf from the set from every input tree, we get a new set of trees, or any combination of leaves, we get a new set of trees, and we can calculate quite easily, just with our original concept, the strict consensus, that set of strict consensus trees. Okay, this second bit is to define, I've put this in brackets for important reasons, is to define strict as the intersection of all largest compatible subsets of strict star. Okay, and when and this is in brackets because in the case of the strict consensus, this is just the same set. Okay, when we look at other methods, in fact, for the majority rule, it's the same set as well. But when we look at the loose consensus, it isn't. And then from that, this can be a very big set, of course. And much of it is too big to be of much use. And so the key to reduced consensus methods is essentially this part. That what they're doing is providing a set of non-redundant trees in strict. And what we mean by non-redundant, I'm not going to explain it in full detail, is that they're trees that are not implied by any sets of more inclusive trees in that set. The sustained here bit is something to do with the numerical values in majority rule, and I can explain that if necessary. We don't worry about that in the case of strict and loose trees. Now, this here is an example from Steele et al. In 2000 in a paper on fundamental limitations of supertree methods. And this is a very interesting example because if we applied this procedure here using the loose approach, we'd end up with an incompatible set. So loose star is an incompatible set. And we don't want that. I abhor incompatibility when I'm thinking about trees. So this is what this is for. This is in order to render the set compatible. And it turns out that this is very important in the supertree context because beyond consensus, not only is this problem that affects the loose method within consensus, affects all the methods beyond consensus. So we have to use this little trick. Now, what I'm going to claim later, and I'm not going to show the slide again, is that after I've developed some extensions to the classical consensus methods that are classical supertree methods, that just by changing the term consensus in here to supertree, I've then defined the reduced supertree profiles. I should clarify that these profiles might have multiple trees in them. And to illustrate that, why would we bother with this? Well, this goes way back from when I was doing my PhD and got motivated by this problem. This is a phylogeny, the figure hasn't come out here, of rhynchosaurs. It's from a phylogenetic study of rhynchosaurs. They're an extinct group of reptiles. Some of the taxa have very little data, and that led to a proliferation of most parsimonious trees and a kind of failing of the classical consensus method. So this is the strict consensus here. And as you can see, it's not very informative. It's got one node in it. Thanks for laughing. My supervisor, whose data set that would appreciate that. More importantly, that one node there is an assumption of the analysis, not a result of it. That's the outgroup. So the analysis produced 22,700 trees. There was no way anyone was going to allow us to publish that, so but we wanted to represent it better than that. So the strict reduced consensus profile includes these 5 trees. And each one of them is summarizing relationships that are true of all of the 22,700 trees. Okay? You can think of each one of these as a strict consensus tree on a set of pruned trees. So for example, in this one here, there's one taxon, the Texas rhynchosaur, which I think had one character, has been pruned, and that's true of all the remaining of the trees that have been pruned of it. Okay. This is another example just to emphasize the point, because I think to some extent we've lived under the tyranny of 2 conditions that people think are really important for consensus methods. One is that the consensus should be plenary, by which I mean it should include all the leaves. And 2, that there should be a unique answer. There's just one tree. I think reduced consensus methods are intended as a way of escaping from the tyranny of these 2 useful, understandable, desirable, but not entirely always necessary and sometimes unhelpful conditions. So here's an example. I'll explain it as quickly as I can. We've got a data set here. Each column of characters was actually, there's 5 of them. And we're going to bootstrap this data. If you look at the data through taxa A through J, there's a perfectly compatible set of characters. There's a pattern there in a tree. You can see it's this tree. But I've added in a nasty taxon X that has, in cladistic terms, the apomorphies for every group. So if we analyze that data with bootstrapping, we're going to get a result and use the traditional majority rule consensus. We get a result, in this case, like this. We've got X over here with A and B. It could have been that X went over there with A and B, and if we did it another time, or 100 times, then 50% of the time it would go over here, 50% of the time it would go over there. So the result here suggests, if we interpret it, that, well, there's no good support for any clades, any full splits. And that's a reasonable interpretation, but if we thought that it meant that there's no good support in the data for any relationships, that would be an overinterpretation. And the majority rule reduced consensus applied to this data produces both this and that. And I think that's useful. Okay, enough of the selling points. So One of the methods that I think might be sensibly used as a supertree method is the majority rule, or generalized from consensus to a supertree method, is the majority rule method. It seems to be a natural kind of thing for incorporating evidence from lots of different trees, where each tree is given an equal vote. And Goluboff and Poll, in a couple of papers, have said that majority rule supertrees are desirable in principle, and they've thought that maybe MRP, one of the ad hoc methods, is a poor surrogate for them, or how we might expect them to behave. But they've said that there's a fundamental problem in generalizing, because you can think of majority rule consensus trees and how we make them by simply counting the occurrence of groups. And they presented an example in which they said it's very difficult to count the numbers of groups when, of these 4 incompatible trees as a set, you can take any 3 and build a tree. But these trees contradict each other in different ways. So if some trees are required to support a group in combination with some others, and some contradict it, the same tree contradicts it in combination with some others, how can we count? Okay, well, the solution, I think, or a solution we presented in a paper this year, was instead of thinking about that way of categorizing the majority rule tree, is to think about generalizing from objective functions instead. And Alan, in his talk earlier, characterized supertrees as trees that minimize the distance or maximize the sum of the fits to the set of input trees in some way. And majority rule consensus trees were known to do that. They are essentially median trees on the symmetric difference on full splits, the Robinson-Folds distance. So all we need to do to generalize the method is to think about generalizing the distance. And that's a lot easier than trying to count splits. So one way we can do that is by comparing the supertree, a candidate supertree, to the input trees by pruning the leaves that are in the supertree and not in the majority rule tree, turning it into a consensus comparison and calculating the distance. Then we've defined our generalization of the classical consensus method. What about the other methods? Well, I'm interested in all of these methods. Partly, I think majority rule methods are very good, but I'm quite interested in strict and semi-strict methods because I'm interested in sometimes in unambiguous agreement amongst trees. And all we need to generalize them in the same way is to come up with a measure, a distance measure, which is optimized by those consensus methods. And this is one way of doing this. So I've defined here an asymmetric strict refinement distance, and it's based really on the idea that when you have a strict consensus, what you're doing is you're removing conflict from the input trees by contracting branches, contracting edges. And you're removing conflict in such a way as to minimize the sum of the number of contractions across all the trees. So we just this has sort of reversed that a little bit, and it's saying it's the minimum number of branch additions needed to convert one tree, the tree induced by the leaf set of another tree, into the tree that its leaf set induces from the other tree. And we can use this then to define the strict consensus method, and we can use it, as it's been written here, to define the strict supertree. This one down below is just a little bit different. Instead of needing to produce the same tree, we need to add branches to imply a tree, and that gives us a semi-strict or loose distance. So my claim is then that we can, using these definitions, we can generalize to the classical versions of the classical supertrees, as it were, and using what I said earlier about the way we can characterize sets of reduced consensus trees, we can complete the project and provide definitions for reduced supertree profiles. Okay, I'm almost out of time, aren't I? So I've got a couple of examples here which I'll run through quite quickly. They're a bit difficult, but this example here, you should be able to intuit what the answer is, what the supertree should be for these two input trees. If you imagine grafting the missing leaf onto here, which is Y, it should go with C. If you graft the missing leaf onto this tree, it should go here. If you take the consensus of those, it's this. Okay. That's the strict supertree. It's the semi-strict supertree as well, because there's no polytomies involved. But in this example, what I've done is I've broken that down into a set of triplets, the triplets that are displayed by those two. And using the methods I've developed, this is the same result you get irrespective of the decomposition. Sort of what you might expect because the information's the same in here. It turns out that Golubov and Pohl, who've also developed a semi-strict supertree method, gives you this result with this, but from here you get nothing. And the reason you get nothing is because the way their method works is it applies inference rules to each of the input trees. So if these are the input trees, it's applying dyadic type inference rules. And if you do that from a set that contains a contradiction, well, classical logic tells you that from a contradiction you can infer anything. So what you get is what's called an explosive inference. And applying those rules, you get every triplet. And then the result is empty. I don't think that's a good thing to do. And I think that it's better to try and remove the conflict before you make inferences from it. Otherwise, you're violating the law of non-contradiction, which is a law of classical logic. Okay. I'm going to skip to the last part, which is about properties and interpretation. So I'm focusing here on the semi-strict consensus, or the loose consensus. I prefer the term loose because Golubov and Pohl have already claimed the term semi-strict supertrees for their method. Okay, now in the consensus case, we can define the semi-strict or loose method, the classical method, in a number of different ways. We can say it's the method that displays all and only the full splits, all and only the full splits that are implied by some tree, displayed by some tree, and uncontradicted by any tree. Equivalently, we can say that it's all and only the full splits that are displayed by some tree and uncontradicted by any set of compatible trees, or by any set of compatible full splits. And we can try and generalize from that to the supertree case, or we can try and generalize within consensus so as to preserve those properties. I'm not going to go into the details, but it turns out that generalizing any of those leads to problems. And my conclusion from that is that they're not the sine qua non of semi-strict methods. They're just special properties that hold in the case of consensus, because the consensus case is a special case. Instead, I think there's this definition, which is semi-strict are relationships implied by the intersection of all largest compatible sets of displayed full splits that are uncontradicted by any tree. That also defines the method, and it generalizes, and it produces a useful method. So the fundamental idea is that I'm suggesting that what semi-strict relationships mean and have a clear interpretation is that they're what are implied by a set of trees after all the conflict has been removed. If you try and find what's implied by a set of trees that contains conflict, you're on a hiding to nothing. And I'm going to stop there. Thanks.
Let's take a question.
Isn't now how the reduced consensus of a tree is embedded in the mathematical sense into the original trees?
Yes. Yeah, it's if you have a set of trees, then that set displays, if you like, a set of subtrees, or many sets of subtrees, which you can produce by pruning leaves from the original set. And every reduced consensus, if it's a strict consensus, for example, is a consensus of one of those sets.
Well, in this case, then there's a general construction that allows you to go from the reduced consensus to a supertree.
I'm not sure I understand, but
it's a general technique to combine the trees into a supertree if you know the subtree, the consensus subtree. Okay,
we can talk about that. Yeah. Sorry.
One more question?
Do you deal only with rooted trees, and when you decompose into triplets, you generate all the triplets induced by every subtree?
For the characterization, I've tried to be as general as possible. So I've talked about things in terms of trees rather than rooted trees. Rooted trees are just the special case in which one of the leaves is a root. That's the way I think about it. Okay.
There is a big difference between rooted and
Yeah, there's definitely big differences, not least computationally, because I mean, one of the things I haven't talked about is how you might find any of these things. So I mean, there are huge differences computationally between rooted and unrooted trees.
Yes.
The characterization I've given is a kind of mental construct to help me provide definitions. It's not actually how you'd go about trying to find the instantiations or apply the methods in practice. You wouldn't break everything down into the triplets and then look at it. It's easier to take intersections of full splits, for instance.
Okay, well, if you don't mind, we'll stop there. But over. Thanks very much.
Thanks.